All right, let's get this started. So, hi, I'm Thomas Morell, and this is my demonstration and explanation of my QPSK bit spreading uh, communication system. So, this is the entire thing from beginning to end, and I'll first give you a walkthrough of the functionality before going into a demonstration. So, this was all coded in uh, Simulink and MATLAB. We have a few MATLAB scripts that go along with the Simulink model, but for now I'll just go straight into the model. So here we have our initial data block, which is our image from workspace. So it goes into um, from the initialization file, which I will open it here. Let's scroll down. Image txrx qpsk frame bitspread rotating init. Make that full screen. So here we are when we run the model, the initialization file, I will show you really quick. Modeling, Model Explorer, callbacks, and we have a preload function and an initialization function. For redundancy purposes, I put this file in both just to make sure it's always going to run. If I make this full screen just so I can show you the whole line. In the preload function, initialization function, they're the same exact line of code. There's literally no difference. And here it says that object variable QPSK TXRX equals, and then the initialization file, which is run as a function. Um, each version of the model, as I will show you here, this is every single version of the model that I have. Some are self-injected transmit and receive because you can see all the TXRX, and some are just receive and some are just transmit depending on which end of the communication system you want to be on. By the way, this is the entire working folder for the model. Inside media, we have, we'll get rid of that, we don't really need that. Delete, cool. Inside here, we have all of the video and photo files that I used. Some are left over from old systems that don't work. Some videos are more ambitious in terms of the data rate. But yeah, mostly this one are used, and these videos can all be ran from the live video model. Let's go back, cancel, back. There we go. So, let me go back to the model. Here, our image parameter is filled with this imread, which just reads the data from that photo black-white 100.jpg image from that media folder that I just showed you. And from there, it gets the RGB matrices. It's 100 by 100 array. Each cell in the array has a value from 0 to 1, or 1 to 250, 0 to 255. Depending on which, I would have a gain to make the data processing easier. But yeah, so sample time here. So this is how many times per second it outputs a frame of this 100 by 100 by 3 matrix. There's three layers because there's one for red, one for green, one for blue. As you can see here, we only take the red portion because it's a black and white image, so all of the RGB values will be the same. So from here, we take the images per second. And right now it's set to 1 second just for ease of use. In the color version of this system, we did optimize the images per second for the best data rate in terms of not just like speed of transmission, but also ease of calculation when it came to the receive end and decomposition of everything. So images per second is also established in, where is it here, in the initialization file. So we have it set to 1. And here we have sim time. Sim time is set to 10 seconds, but that isn't being used in this model as of right now. Let me just select OK. Here, right now, the stop time is set to infinity, but if you want to have a coded in stop time, we could do the QPSK TXRX dot sim time, and that would be set to whatever you put in that parameter in the initialization file. So, is that it? Yep. Here we could choose separate color signals or one multi-dimensional signal, but I have it to separate because we only need one. And we can save the computer all of the work that it would take to decompose the 100 by 100 by 3 matrix. All right. Then it goes into a video viewer which also is just an image viewer. This is just to make sure that you're sending the right image from the transmit side. So from there, I send this 100 by 100 matrix into a reshape block, which takes each vertical row of the matrix, rotates it by 90 degrees, and then concatenates them into a straight line. Sends that 10,000 pixel or 10,000 integer array to the integer to bit converter, which converts those integers into 8-bit values. Unassigned with the most significant bit first, and set to double. So now we have 80,000 bits passed along this signal. Let me just triple check that my mic is still recording. It is. Fantastic. Then we send it to a buffer, which buffers the data into our payload length. The payload length is also established in, where is it? This file. We can go down here, and the payload length is going to be our height of the image, which is 100 pixels vertically, times 8 for 8 bits, times 2, because we are able to fit in our data block 2 of those 800 bits strips of the image. So instead of having 100 packets of data, so 1 packet for each strip of the image, we now have 50 because we're sending 200 bits or 2 vertical strips of that image. So then once that's buffered, we send the 1600 bits into our frame builder and modulator. And here's where we build the frame. So essentially, all of this is to put the frame together. Here we have a frame counter, which tells you which frame in the total message is being sent. So here we have a counter that counts up. It's free running at a sample time of 1 divided by the frame count times the images per second. Yeah. And let's see. Since we have 50 frames to send the whole image in 1 second, it's 1 divided by 50, so you have 0.02. This goes into a modulo because this has no limit. It just keeps on going until it reaches the 32-bit integer limit. So then we set it to a modulo, which sets the denominator to the frame count, which I said is 50. So that every time the counter hits 50, it goes back to 0, counts up, goes back to 0, counts up to 49, goes back to 0, over and over again. Because we have a circular or rotating transmission. So it just keeps on looping the same transmission of the image over and over and over again. And I could show you that logged in a visualization later. set to an integer the bit converter at 16 bits, and we add that to the front of this matrix or part of the frame. Here we have the frame count, which is going to be 50. Boom. Convert that to a 16-bit integer, sorry, 16-bit string. Add that. Payload length, which is the amount of bits in the data block we're going to use. So we have our 1600. Convert that to an 11-bit number. Concatenate. Here we have our input data in this in block, which is our 1600-bit buffer, or the two strips of the image. And then we concatenate that with the payload pad. And all the payload pad is a pad of zeros that fills out the rest of that data block to add up to the 1715 data bits in our block. So I can show you here, since our data block is 1715 bits long, we have to fill it up because right now our payload length is 1600. And let's see, payload pad, we can see here is established with zeros, which that command just fills a zero string. And then we input the size, which is the data block length, 1715 minus the payload length, 1600, over the first dimension. All right, so going back to our system. Once those are concatenated, we now have our 1715-bit data block, and those are all concatenated. Here, we establish a checksum. So it sums up all of the bits in that entire array and converts that to an integer to another bit value that is 12 bits long. And then that is concatenated with the data and sent along to the bit spreader. Before I go to the bit spreader, this is where our rotation is established for the rotating bit spreading sequence. Right now, I have it set to a constant 1 for computational purposes and to show you the operation of the bit error rate calculation. As of right now, with my laptop doing self-injection, it can't keep up the bit error rate calculation with the rotating bit spreading sequence, but I can show you that the system still works with this working later on. So right now we have a constant 1, convert that to a 4-bit, that integer to 4 bits, and we send it down to the bit spreader. Now here is the total bit spreading block, and we have our 4 sequences, and this is the input for that counter value. Here we have our data coming in, and we put that from unipolar to bipolar. So instead of zeros and ones, we have negative ones and ones, because that is, as you can see, how the bit spreader operates. And it works when it comes to doing the arithmetic that determines whether you have a 1 or a 0 with confidence. This is a pretty easy block. We have our M area number set to 2, because we just want 1, negative 1, positive polarity. So 1 will be a 1 and 0 will be a negative 1. Then we buffer that for 1 bit, because now we're going to multiply each bit by its sequence. So here, we select which bit spreading sequence we will use, depending on the incoming rotating value. So I have the system set up where we have 4 spreading sequences. So if there's a 1 in each of these boxes, it'll select one of these spreading sequences. So right now, since we have a 1 in the very front, we're going to select this spreading sequence. So these selectors select each of these bits. So this one gets this one gets this one, so on and so forth, until we get to the last one. And these right here are enable switches on top of these spreading sequences. And so when this one has a 1, this 1 gets uh, sent as a logical value to the enabler, which turns on the spreader. When the enable is 0, this these blocks are disabled. So only one at a time can be enabled. And when one is enabled, it allows the data or the bit from this buffer to be sent into that spreading sequence. Once it's inside that spreading sequence, we have an input here, and that bit gets multiplied by the sequence. So we have 1 times 1, 1 times 1, 1 times 1, 1 times 1, and that's all concatenated into a 4-bit array and sent out from here. Pretty simple. Once it's sent out, we can see it gets selected into the output sequence, which converts it from bipolar back to unipolar with our 2 M-ary number. And I have a checker here just for debugging purposes that if the value output is less than 0, you stop. Because it's bipolar to unipolar, it should never be 0, because that will break the system. After that, it gets sent to the buffer, that then collects all of the bits from the original incoming data sequence. And logically, if we have 1,770 bits coming in, and we multiply each bit by a 4-bit spreading sequence, we should have 4 times 1770, which is what we have here. And that's established in the initialization script with the name frame length post spread. Pretty self-explanatory. That is calculated over here, and that's just our frame size, our total 1800 bits minus the 26-bit header, well, Barker code here, minus our 4-bit sequence selector value, and that's times 4. So, see that. Bada bing. That gets sent out. Actually, let me just make sure I didn't skip anything here. So, here we have a switch that is kind of mandatory when it comes to Simulink, when it comes to the very specific way it has to process signals. And the way I have it working is that we have 1, 2, 3, 4, and then default, which just defaults to a 0. And as we can see, right now we just have the first selected. So we have the first bit spreading sequence selected. So this switch should be on 1, and we can see that in this display it says 1. And how I have this working is that since only one at a time each of these streams can be a 1, we just multiply that 1 by the corresponding spreading sequence number. So 4, 3, 2, or 1. And so 1 times this gets sent into this addition block, which just adds that value, because everything else will be 0. Because let's say we have 1 here, 2 times 0, 3 times 0, 4 times 0. So we just have 1. That 1 gets sent to the switch, and the switch is like, all right, I got a 1. I'm going to switch it to 1, send it down the line. I wish I could show you it working actively with the rotating sequence, but this number will change every second when I do that, because I have the spreading sequence set to changing every second. So I'll show you that when I have the rotating input. All right, so now our data is going out after the buffer, and then it gets sent to the scrambler. The scrambler sequence, polynomial, is set here with initial states of 0 and calculation base of 2. These values are also set in the initialization script down here, but they are currently hard-coded into the system. That can be changed, though. You just put QPSK txrx dot and then the variable name. which would be scrambler polynomial and stuff like that. All right, and excuse me. Up here we have the unipolar Barker code, which takes the Barker code from the initialization file and sets it to unipolar, and then it repeats it twice. It repeats it twice for modulation purposes. If we were doing 8 PSK, it'd be repeated 3 times for the 3-bit per symbol constellation, and for BPSK, you wouldn't have any repeats for the 1 bit per symbol. These are all concatenated because you want your header to detect the frame. You want your bit spreading key to be able to decompose the bit spreading sequence or the bit spread bits, and the data, scrambled data. That totally concatenated packet is sent through QPSK modulator. Open that up. Input type is bit with gray coding and a phase offset of pi/4. Um, to be honest, I think intuitively you would think this would be the default, but for some reason the default is a phase offset of 0, so you end up with a constellation with 2 points on the real axis and 2 points on the imaginary axis. So we have to make sure that it becomes this square sequence like this instead of a diamond. We send that through the raised cosine square root filter with all of these parameters set in the initialization file for sets over here and here. Interpolation is decided here, and decimation is decided here. All right, and then we output our data. Now I have a simulated AWGN, additive white Gaussian noise channel, because when the radios are connected, it really makes no difference because the radios are just plug and play. But I can show you a file, and I will show you a model with the radios in it so you can see the input parameters. But right now, with the channel, I just have the signal to noise ratio set to 20, and the power is set to 1, with the RNG set to global stream and code generation. After that, it's sent to another raised cosine receive filter with the same parameters. And here it's sent into the frame synchronization subsystem. Here we determine that we have our QPSK modulation, correlation-based estimation algorithm, and a maximum frequency offset that is decided in the initialization file over here. And that's hard-coded, no calculations. The frequency estimation is sent through a running average, and it's flipped to the negative, and it's sent to the phase/frequency offset block, which has a dialog parameter of 0, because the frequency offset is from the port, and it calculates the rest on its own. That value is output into the simple synchronizer. With these parameters, we are on PSK, Gardner timing error detection. Here is our samples per symbol, which is our interpolation divided by decimation, which I just showed are in the initialization folder. We have the phase recovery damping factor, also in the initialization, phase recovery loop bandwidth, and timing error detector gain. And I could show you those are here. The gain is calculated here, and we will get to this in a little bit. Now, this signal is sent into our carrier synchronizer. Once again, QPSK, phase offset set to auto, samples per symbol, damping factor, normalized loop bandwidth. That's sent into an AGC, a desired power of 1, so that we line up our constellation um, with exactly 1 power. We average over 100 samples of data, and our maximum power gain in dB is 60. After that, we have essentially our completely cleaned up input signal, and we're ready to detect the frame and decode the data. And this is where I put a constellation diagram just so we can see how the cleaned up data is looking and make sure that we properly synchronized with our input signal. So this is sent into the frame synchronizer. Here we take our Barker code for the preamble and we multiply it by this factor, which takes which maps the bits onto the constellation. Because right now this is just bits of -1 and 1 essentially, and multiplying it by this factor over here maps it onto the um, the complex plane, so that it can detect it from this complex data. Then we set the detection threshold. I manually set it to 7 because that just worked best. The default is 20, and our output length is our frame size of 3555, and that is set in the initialization frame size here. So when it catches a frame and detects the preamble, it sends a Boolean 1 into the data decoding, into this enable switch, so it enables the data decoding, and it sends that 3555 frame to there. And here we have our data decoding system. So we have our data coming in, and it sends it to this phase offset estimator, which takes our Barker code symbols. So it takes the Barker code, repeats it twice because it's QPSK, modulates it. So now we have a reference Barker code waveform. So here we take that reference Barker code waveform and we select that Barker code waveform from our output frame. So this is the index of the selector, which just grabs a selected amount of bits from the incoming frame. So we take the first bit all the way to the length of the Barker code. Barker length is also established here. And then it compares them over a correlation. And whatever change it gets, it gets the complex to magnitude angle value, and then it detects the phase offset in this script over here, and then it outputs that phase difference. That phase difference is sent into the phase ambiguity correction and demodulation block, which takes the data and the phase, does complex phase shift, and finally demodulates the signal. This is a set block, so you don't have to worry about parameters. And here we have bit output, hard decision type, gray coding, and the pi/4 phase offset. That is sent into the descrambler, which selects everything after, sorry, first it takes the first 4 bits after the header, because those are our rotating bit spreading sequence value. And we need to keep that because those bits weren't scrambled. So we're keeping that and saving that from the frame. The rest of the bits are taken out. So everything after the spreading sequence value is taken out. Sent to the descrambler, which has the same polynomial and initial states. Reconcatenated and output. That output is sent to the bit despreader. Just triple check, microphone's still working. Fantastic. And from here, we reselect those 4 bits of the spreading sequence value. And from there, it is selected, or it's selected out of that array and chooses which spreading sequence to use, as I explained earlier. But these despreaders take the 4 bits that have been spread, selects one from one from the 4, multiplies them by the spreading sequence, sums up the values, and if they're greater than 4, if they're greater than 0, the maximum of 4, it's a Boolean 1, so it just sends 1, and then it converts it to a double from Boolean. And if it's less than 0, at a maximum of -4, it sends a Boolean 0, and then converts that to a double of 0. And just to go back to here, we select all of our data besides these 4 bits. As you can see here, this outputs 4 bits, and this outputs 7084 minus 4, so 7080. Converts it from 1s and 0s to -1s and 1s, or respectively 1s and -1s. Buffers them into the 4-bit sequences because 4 bits now represents 1 bit. Down here for debugging purposes, I just have a small list of the converted data. And the switch selects which despreading sequence is currently being used, outputs it into the buffer, and the buffer saves the amount of bits that were in the frame before the spread. So now we're back into our 1770 size frame, and we output it. Let me just triple check. Okay, yeah. So on this end, I output the number of the bit spreading sequence, so 1, 2, 3, or 4, Yeah, I just have a little display here, so we could tell with the rest of the data in our dashboard which sequence is being used. So now we have our data that is being output into the checksum and also the bit error rate calculation. Inside the checksum, we select all of the bits after the bit spreading key, so 5 to the end of the frame. So we have 1800 total frame size minus the barker code minus the frame count value minus the key of bits. 12 should be frame count value, if I'm not mistaken. 12. Oh, of course, it's the checksum value. You don't want to have the checksum value inside that calculation because that's added on after checksum is performed. So we have our total frame minus barker code minus checksum value size minus bit spreading key size. Here we select all the bits after the data that doesn't include the checksum, because now we're just taking the checksum bit representation of the integer value from the frame, so 1 through 12, converting it from a bits to an integer, and here we're adding up all the data, and we're seeing if they're equal. As you can see here in the saved paused version of the model, they're equal, and that boolean is sent out, and the frame is sent out. That boolean 1 here enables this block, which is the frame number check block, and here we have our data being input into it. So here we select the frame number bits, which are just the first 16 bits of that frame, converting it from bits to an integer, and sending it into this comparison block. Now here we have our number received. And so what this loop does is it checks the number of the frame that we're receiving and making sure that it's in the order of the proper order of reception. So if we get frames 1, 2, 3, and 4, and then 6, we're going to ignore that 6th frame reception and wait until the cycle repeats on the TX side, and wait until we get the 5th packet again. And then once we get the 5th packet, it'll add it to the received data, and then we'll keep on receiving packets 6, 7, 8, 9, 10, and so on and so forth. So if they're equal, it increments this counter, which is set as 0 to 1 initially. So let's say the first packet comes in through here, and this one is 1. It compares them, and if they're equal, it increments this again, and it keeps on incrementing and incrementing and incrementing until they're not equal. But for as long as they are equal, this operation over here sends a Boolean 1 to enable the next area, which is the approved frame decoding block. So these incrementers over here count the Boolean outputs to enable certain blocks. So this counter counts the enabled of this one counts the enabled of this one. So sometimes we'll get a good checksum, as you can see here, because we have less valid frame numbers than checksums. So we'll have a good checksum, but that doesn't mean that we could use that data because it might not be in the proper order of frame reception. So here we lost one frame in the reception, and we couldn't enable this one. We had to wait for the next frame to come in. Now, sometimes, as a side note, when the computer is calculating too much and it's overloaded, the enables stay locked in a positive position. So sometimes I'll get a higher number up here than down here, which doesn't make sense. But sometimes that happens if the computer calculation steps are too high for the logic to keep up. Which is also why I had to set the rotating bit sequence to just one constant, because the bit error rate couldn't keep up and with the switches. So once we have this approved, it enables this block and we send our data in. And what this block does is reconstruct our image. So here we select our data. So this is selecting the entire data block, the 1715 large block. After that, we select our 1600 bits of data. And here we convert the 1600 bits into integers again, because we had our 8-bit integer representation, to our 200 bits, 200 values, or 2 strips vertically of the image. That's sent into the buffer to catch the height of 1 strip of the image. Then that is converted from a column vector to a row vector between these two. Then that's buffered over the width. So all we're really doing is capturing that height and then sandwiching them on top of each other for as long as the width. Then we flip the columns and we rotate the image by this angle, just by how all of the matrix calculations work out. This has to be done to correct the image. And then we put a gain of 1 over 255. And output that 100 by 100 frame. Send it to all 3 channels because all 3 channels are equal in a black and white image. And then it's sent into the video viewer, which finally shows that image. At the same time, we capture the matrix and output it to the workspace, and we also stop the simulation. This block here is just a frame rate display for when we were doing videos. I'll go back in the data decoding for a second to show you the bit error rate calculation. Here we create an artificial frame, which is just a reference frame, to compare the incoming frame with. It's the same architecture as the TX. Then we put it into the bit error rate calculation. Here I have it set to select a static number from the array, or from the frame, which will be the frame count total, which is 50, and it'll always be the same. So if there's an error, if there's a discrepancy in this, it'll be easier to get and to catch. The reason I have it set to such a small number of bits from the frame is because when I try to have it catch the proper frame number, the calculation time problems were just causing too many problems for myself. And I decided to make it simpler and just catch those 16 bits, compare them, and output the error rate. But I can imagine with a more powerful computer, it would be easier to implement that more robust system of comparing entire frames. All right. So now I'll do a little demonstration showing this system in action. All right. So now, if I go to, how should we do this? Let me disable the stop. Go to data decoding. I'll show the error rate calculations. All right. So as we can see, we have what this display says is that this is our bit error rate at the top level. This middle level is the amount of bits that were wrong, and this bottom level is the total bits received or really calculated. Many more bits have been received than this, but this is just incrementing 16 bits over each packet received. So we have 8 bits and nothing more. So those come in when we initialize the system, but after initialization, as you can see, it holds down pretty well, even with our simulated noise. And I can imagine as you decrease that signal to noise ratio towards 1 or even less, but it'll really increase that bit error rate. But I set it to this value because when we had real life testing over free space with the Pluto SDRs, this is what our constellation looked like for the most part when it was fully synchronized. So here we have a display of the index of which bit spreading sequence we're using and staying at 1. Here we have our total packets received. And here we have the number of packets that came in incrementally. And if I take a look at the data inspector, I really hope this is working right now. Fantastic. So what you're looking at here is a orange line and a purple line. The orange line is the um, packet number that's being extracted from the incoming packet. So it's a number from 0 to 50 that's being incremented over the packet transmission. So each triangle you see here, each triangle wave you see here is one image being fully transmitted. So we start at 0 and it goes up to packet 50 and the image is completely set and then restarts from the beginning. The red line is, the purple line is the number of packets received in succession. So we make sure that we get all of our packets in order, and as you can see, for a while now, it's been sending in perfect unison. And I can't seem to find a spot with any errors. Oh, nope, not even then. All right. All right, beautiful. So I'm gonna stop this now. Zoom in on here for a second. So the purple line, like I said, is the packet we're waiting for. So right now, here, it's waiting for packet 0. And here, the received packet number dropped down to 0. When they're both equal, the counter counts up by 1. And now we're waiting for the 1 packet. We receive the 1 packet, the expected packet jumps to 2, and we wait for the 2 packet. We receive the 2 packet, and we jump up, and so on and so forth, until we get to 50. As you can see here, over time, our bit error rate decreased to 0.0001, and if we waited longer, eventually it would just get closer and closer to 0 because we maintained that 8-bit errors. Now, I'm going to comment this out to save the computer the power, and I'm going to set the rotating bit sequence. So in order to get that 4-bit array to look like this, and to switch the 1 in each significant bit spot, instead of just counting up from 1 through 4. Because obviously, if it was a simple bit counter, it would be, for 1 be 1, then for 2 would be 1 0, then 1 1 for 3, sorry, 0 for 1, 1 for 2, 1 0 for 3, 1 1 for 4. Instead, though, I want to be able to, let me do back to that, have it go from 1, then 1 here, then 1 here, then 1 here, with the rest being 0 each time. So what I did is I have a counter here that counts up to 3, and every time it counts to 3, it goes back to 0. And here, I have a 2 to the input calculator. So if our output from the counter is 0, we have 2 to the 0, which is 1. Then we have then we send that to the integer, the bit converter, and that outputs 0 0 0 1. If we want to have the second index, we want 0 0 1 0, right? So then we have a 1 come out of here, that gets sent here. 2 to the 1 is 2, and now this sets it to 0 0 1 0. If we want 0 1 0 0, we send out 2. 2 to the 2 is 4. Then it converts it to 0 1 0 2. Yeah, 0 1 0 0, and so on and so forth. All right. Now that that's implemented, I'll start running it. So here, as you can see, the seconds, since this is completely being run on the computer, it's a little slower than real time, but in real life application, every second it's changing the sequence, as you can see here. Oh, okay. And here you can see the integer value go up. And then it's being output. Here we could see on the receiving end, we're receiving our 1, 2, 3, and 4, our successful packets, and our successful succession packets. If you look at the data inspector, we can see we're receiving that data. I don't know what this erroneous counter is, but if we look at the image received, it's the right image. I can run it again to show you. Just allow me to put on the stop. All right. So now we want to implement this into the app scenario. So what we're going to do is open up two instances of MATLAB. We have one open here, and we have another open here. Now this is because we can only run MATLAB scripts, like M scripts like this and this, one at a time per MATLAB instance. You could also, per MATLAB instance, run one M code script and one Simulink model. So here I have I have three total files open, and I'm going to close this file for now. I have this file, which is our rxsim underscore new.m, and this runs our Simulink model automatically, saves the image to our files so that it could then be read by the server and displayed by the app. Here is our server file, and the server file connects to a local port on the laptop or computer and communicates with the app that was coded in uh, Unity. So to start off, and also these files are also in the base file of the project. Here we have rxsim and rxsim-new. So we start off by launching the server, and then here, the only thing you have to change in this file, depending on what you want to do, is this file name to target the specific Simulink model you want to run. Right now I have it set to STL Sim Image TXRX QPSK frame Bitspread rotating, which is this model. If you wanted to set it to just so let's say you wanted to send out, um, or you want to receive an image, not a video, and you wanted to receive it in color with the rotating bit spreading sequence. Here we have image, receive, bit spread, rotating, color. And you would put that name into this string right here. Keep in mind, only the receiving end has to run this. Let's say you're transmitting. All you have to do is open the matching model, load it up, click run, and let it do its thing. The TX and RX pairs have the same exact names, just that one says TX, one says RX, and the one that has both is the self-injected, like I just showed you. So we have our name of the file in here, and let's open our app to open the image received file, new design app.exe, and here it is. So we're gonna leave that open and not click any of the buttons yet. And I will run this receiving script. So the script is now going to run this model and receive the image, as you can see here. Now that we have received the image, we're going to open the receiving app and click Establish Link. and here it is. Now, one error that has come up with the way in which we save the image is that sometimes it doesn't save. Well, when we use the save as command, it doesn't save as 100 by 100. It saves whatever this frame is, which is greater than that, as you can see. I'm going to try to change the code right now to see if I could fix that error, actually. Oh, I can't pause. Alright, I'll just edit it out. Hmm. Alright, so I've rewritten the code to have I am right instead of or am right instead of save as, and it successfully changed. So now, when I run this system, it's going to run the Simulink model, and we'll receive our image here. And then instead of save as, it'll do im right. And when we use im right instead of save as, it'll save this portion of the figure instead of this entire window, which was our problem. So now it'll display it perfectly square. And let's say you want to change your image. You go to your initialization file, which will have the same name as the system model you're running, except it'll have TXRX. So we want sim image TXRX QPSK frame Bitspread rotating initialization. Let's say you wanted color, you would go to the color initialization, but now we're just using black and white. So let's open that file. Now let's change our image. Let's see what our options are. Let's do Mario. Save it, close it, run the script. received. Go to the app, updated. And that's it. That's how the system works, beginning to end. If you want color, it's the same process. I just won't demonstrate it now because it's too much for the laptop to calculate, but it is the exact same process. The initialization file is nearly identical, so is the model. Now, I'll briefly show you the radio inputs for the Pluto SDRs. I don't seem to have a radio. Alright, I'll just use one of the RX. Okay. So, close this. Yes. Stop this. This. So I will open this one. And for TX, open this one. So on the TX side, after your frame builder modulator, your data goes into the Pluto with these parameters. Your sample rate is calculated in your initialization file as well. And here we have just an underflow output. So if there's any underflow, the radio can't keep up with the data coming in through Simulink, it'll send out a 1. That's all that does. On our RX side, we establish our center frequency, sample rate, and samples per frame, calculated here, frame size times interpolation. And yeah, here we have an overflow indicator, and that's it. So that is essentially the system from beginning to end. Thank you for watching the video, and I apologize for being so long, but to get that much detail, it was necessary. If you have any more questions, please let me know, and I would be absolutely happy to record another video with any specifics that you would like to know more. Thank you.